Hello everyone, I'm Xinyang. Today I will share our project, which is called Paragraph to Image to you, and our team members are Shuowei, Xudong, Decang, and me. Well, first I want to introduce our motivation. When we want to let others know the picture of what we have in mind, we will express it in words. We want to use large paragraphs to describe the details on the image. For example, the style items on image. When we are searching for an image, we also use this approach. However, in many existing software, this requirement is difficult to meet. That is because there are two general problems with many of the current software. Firstly, they do not support long text, and second, they do not work well on unlabeled image. The first question here: when people want to find the image more exactly, they may provide more information to search it, but sometimes it will result in a worse performance of matching image. Some of the more common jobs currently available, such as Google search, they will use the text matching for image recognition. Recognition. They will match the text you type in their own image library and then search for it. However, this leads to a problem that all words have same weight, and many key information and logical associations will be missed. Here is an example of Google search on a given paragraph. The paragraph is upon the mountain's rising ground, ever upward into sunny rays, there is a feeling of peace as foot meets earthy path. The ideal matching result is the former, but the result of the Google search is really bad. Well, the second problem is the unlabeled data. When the data have no caption, the matching cannot be exactly. For example, I have thousands of images in my local photo gallery on my photo or maybe on my computer. And there are two images about cats. The first one is labeled and the second one is unlabeled. I use the search function, and no matter how I describe it, I can only find the first image. The second unlabeled image will never be found, even though that it is much better to the paragraph. This is certainly a serious problem. So the wrong match and label data are two main problems in current text to image software. We want to seek for a powerful tool for matching long paragraph to a labeled real image. Based on these reasons, we proposed our paragraph to image application, which can caption the image automatically and match the paragraph with the image perfectly. Well, we can move the next part. I want to introduce some sort of background firstly. We will choose framework to achieve our application. First, we introduce an important recent work on image captioning. It is excellent. X linear attention block will calculate the low rank polling at first, as shown in this figure. Then, two kinds of bilinear attention distribution will be calculated to aggregate both channel and spatial-wise information. After that, a screen's aggregation and self-gating mechanism will be applied on the following layers of these two parts, which dynamically adjusts the attention value feature V. By doing this, excellent attention block can capture the second feature interaction. For high-order feature interaction, we can use our X-linear attention block to iterate over the above bilinear attention mechanism and feature aggregation process blocks. In the excellent, another part is faster RCNN. It is firstly utilized to detect a set of image regions. Next, a stack of X-linear attention blocks are leveraged in the image encoder to encode the region level features. Depending on the enhanced visual features, X-linear attention block is further adopted in sentence decoder to perform multimodal reasoning. This encourages the exploration of high-order intermodal interactions between visual content and natural sentence to boost sentence generation. The second framework is BERT. BERT is a language representation model that maps a token sequence into a vector sequence. It consists of a stack of transformer encoder blocks. BERT is designed to pre-train deep bidirectional representations from a labeled text. As a result, the pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-art models for a wide range of tasks or applications, such as question answering and language inference. This figure shows overall pre-training and fine-tuning procedures for BERT. Apart from output layers, the same architectures are used in both the pre-training and fine-tuning. The same pre-trained model parameters are used to initialize models for different downstream tasks. Well, the overall of our application is shown in this figure. Basically, we perform a matching between a paragraph and an image by matching their latent representations. For image, we use the generated caption. For text, we use these key components. In the following slides, we will describe how we generate a caption for one image and how to extract keywords from one paragraph. For each image, we seek for a good caption. 2 steps is needed for captioning an image. The first step of captioning is to detect the objects in the given image, and transform them into regional features. A pre-trained fast RCNN model is used to do the object detection and generate bottom-up features. Those bottom-up features are used to feed the caption model for further analysis, and the caption model will generate the captions for the image. For each paragraph, we seek to generate the keywords and the key phrases for it. The basic idea is to embed the paragraph to get a document-level representation via embedding models. Then we can get the n-gram words or phrases via extracting the work embeddings. Eventually, we find the most important words after similarity measurement. Upon getting the embedding of key components of a paragraph, we can match embeddings of the text and the image caption to find the closest one. We will use the keyword to implement this. We do several experiments to evaluate our models. We use 2 datasets for different workflows. The COCO dataset has 80,000 images for training, 40,000 images for testing, and 40,000 images for validation. It includes many of the objects with have 80 object categories and 91 subcategories, and each image inside it has more than 5 captions to describe. Meanwhile, we will use the Unsplash to augment our image database. The Unsplash unlabeled version for commercial and non-commercial usage includes 25,000 nature photos. All of the photos in the Unsplash are from all over more than 215,000 global photographers. We will use the well-trained excellent model to generate captions based on the unlabeled Unsplash datasets to verify generating quality. Since the Unsplash dataset consists of real photographs and illustrations widely used in books, videos, and creative slides, we think the test result can reflect the real performance of our application in a practical scenario. Well, firstly, we evaluate the image caption generating use COCO testing dataset. The CIDR score is one of the most credible assessment criteria for image annotating. The excellent achieves 122% with CIDR score optimization, which approaches or even exceeds the state-of-art caption models such as the LSTMA and UpDown. In practical, we want to automatically generate captions for a series of images to augment the image database or manage the personal image site. A high CIDR score means Excellent can achieve this goal with a high quality performance. Secondly, we try to use the model to generate captions for Unsplash datasets. Since we do not include Unsplash into the training site, it could reflect our model performance in a real scenario. We tested our model by separately captioning the landscape photos, object photos, and portrait photos. We find Xline can capture key features and transform them into one descriptive sentence. For example, the model output aerial view of mountains covered with snow for the first image, which describes the relationship between snow and mountains and the shooting angle. Therefore, we think Excellent can be applied with high accuracy and performance to the practical applications. The final target we want to achieve is matching the image paragraph with several most relevant images. Note that the writers always use a search engine such as Google or browse a professional photography website such as the Unsplash to find suitable images in the real world. Therefore, we compare the results from our system with searching the keywords or entire paragraphs in Google and Unsplash. The results show that paragraph to image gets more relevant and more suitable results. For example, the key features in the paragraph upon the mountains rising ground ever upward into sunny rays. There is a feeling of peace as food meets earthy paths, mountain and sunny. The resulting image of paragraph to image describes a scenery, including both sun and mountain, which is more relevant to the given paragraph. Since it is difficult to summarize the keywords of the paragraph, the search results from Google and Unsplash both missign. Well, in conclusion, we successfully designed an application called Paragraph to Image, which automatically illustrates descriptive text to meet the needs of textual workers. We reproduce part of the accent code and combine the keyword to form the whole application. The result shows that paragraph to image can alter the size of images with high relevance to the input paragraph. Well, this is all of our project. Thank you for listening.